Okay, today we're really wading into a big one. Fundamental clash, you could say, right at the heart of AI development. And our guide through this is, well, a true giant in the field,
Yeah,
Richard Sutton.
that's right. I mean, when you talk about the foundations of modern AI, especially learning systems, Sutton's name is just essential. He's a founding father of reinforcement learning, or RL. He invented absolutely crucial techniques like temporal difference learning, TD learning, and policy gradient methods. And, he got the Turing Award for it, which is basically the Nobel Prize for computer science.
Exactly. So when someone with that kind of background, that kind of foundational role steps up and says the current trend, large language models, LLMs, the whole generative AI thing, when he calls it a potential dead end, well, people notice. It's a really strong contrarian view compared to where the industry seems to be heading.
And that's what we want to dig into. Why does he say that? Sutton sees a fundamental split. The LLM way, he argues, it's mostly about mimicking people, predicting text tokens based on huge data sets. But the RL way, the one he champions, is completely different. It's about understanding your environment, acting in it, and actually achieving real goals. These are just two competing philosophies about what intelligence is fundamentally and how we should go about building it.
Okay, let's unpack this. So let's start with that core critique, the architectural one. We see LLMs doing amazing things, right? And the natural assumption is, wow, they must have built these incredible models of the world internally. Why does Sutton push back so hard against that idea?
Well, his argument is that LLMs are brilliant mimics. They mimic the output of things that do have a world model, namely us, people. But he argues they aren't building that kind of robust causal model themselves. The key difference for him comes down to prediction. What are you predicting? A real-world model, one that learns from experience like Alan Turing talked about, lets you predict what will happen in the world if you take an action. LLMs, though, they're optimized to predict what a person would say next in a sequence. It's about communication patterns, not necessarily about environmental consequences.
Ah, okay. That distinction changes everything, doesn't it? Because the system is just predicting the next word in a chat. There's no built-in check against reality. No ground truth, as they say.
Exactly. Without a goal that actually involves interacting with the world, whether physical or digital, how do you define right or wrong? Better or worse? There's no independent standard for your knowledge. Reinforcement learning, on the other hand, it provides that ground truth right away because the whole point is to get rewards from the environment. So the right thing to do is the thing that gets you reward. Simple as that, almost.
Which makes the RL system inherently self-correcting against reality. And without that kind of check, you lose something Sutton emphasizes, the mechanism of surprise.
Right. He argues LLMs can't make substantive predictions about the world because they aren't fundamentally surprised when something unexpected happens out there. They just see it as more input data, another part of the sequence to predict from. An RL agent, though, if it takes an action and the world responds differently than its internal model predicted, its value function calculation is immediately wrong. That discrepancy, that surprise, forces an update to its knowledge. The LLM just sees the unexpected event and tries to predict the likely human response to that event. Different focus entirely.
I see. This ties directly into how we even define intelligence. Sutton often references John McCarthy's idea that intelligence is the computational part of the ability to achieve goals. So if we take that definition, why isn't next token prediction a real goal? I mean, it's a huge, complex optimization task.
Yeah, it's a task, but Sutton argues it's not a substantive goal in the McCarthy sense. The difference is about agency, about influence on the world. Predicting tokens is, well, passive in a way. You're predicting stuff that comes at you or follows from what you started. You aren't necessarily changing the external world to achieve some persistent state. A truly goal-driven system needs to act on its environment, and the results of those actions need to feed back into its learning. If you're not changing the world outside the text stream, moving a robot arm, say, or completing a complex task in a database, you're not goal-driven in that fundamental sense.
Okay, but here's the counter-argument you hear all the time, and it sounds pretty practical. Why not have the best of both worlds? Use LLMs as a fantastic starting point. Give the system a massive head start with all that human knowledge via imitation learning, and then turn on the RL, the experiential learning, later. Doesn't imitation provide a really good prior, a good foundation? What's Sutton's take on that?
This is where he brings out his famous bitter lesson. It's something he's observed over decades in AI. The bitter lesson basically says that in the long run, AI methods that lean heavily on baking in human knowledge or human-designed structures, like imitation learning. They almost always get overtaken by methods that are truly scalable, methods based on raw computation, general learning principles, and massive experience.
So even if imitating humans gives you an early advantage, you're kind of setting yourself up to be bypassed later. By those who just focused on the scalable experience-first approach from the start, why is relying on human knowledge potentially a trap?
Well, Sutton argues it creates a kind of psychological trap, and an architectural one, too. Researchers can get sort of locked into optimizing the human data, refining the structures they build based on human intuition, instead of focusing purely on the underlying general mechanisms of learning and search that actually scale up massively with more computer power and more experience. He points out that historically, the teams that focused on those scalable general principles are the ones who eventually eat the lunch of the teams stuck on the human knowledge approach.
That really frames learning from direct experience as the more fundamental, maybe the more natural path to intelligence.
He definitely sees it that way. And he makes this quite provocative claim, supervised learning, where you give the system explicit examples of this is the right answer or this is the right behavior. He says that just doesn't happen much in nature. His great example, squirrels don't go to school.
Right. They don't get labeled data sets telling them this is a good nut, this is how you should jump. They learn perfectly well from just trying things and seeing what happens.
Exactly. Animals, babies, they learn through trial and error, through prediction, through consequences. They interact with the world. They build internal models based on what helps them survive, what achieves their implicit goals. That's the paradigm he believes the truly scalable method needs to follow.
Okay, so let's get a bit more concrete. What does that scalable experiential paradigm actually look like architecturally?
Sutton describes it as this continuous, lifelong stream. Sensation, action, reward. That's the input. The learning happens from that stream, and the knowledge the agent builds is about that stream. Specifically, it learns the connection between its actions and the sensations and rewards that follow. If I do this, then that is likely to happen. It requires an architecture built for continuous online learning.
Makes sense for immediate consequences, but this raises a classic challenge for RL, those long-term goals with really sparse rewards. The reward might be years away, like your 10-year startup success example.
Yeah.
How does the system learn which actions, taken way back when, were actually helpful?
Right, that's the credit assignment problem. And it's where temporal difference TD learning comes in. It's absolutely central. TD learning uses something called the value function. This isn't the immediate reward itself, it's the agent's ongoing prediction of the total future reward it expects to get, starting from its current situation and acting according to its policy.
Okay, walk me through how that works. Let's say 5 years into the startup, I land a key partnership. No immediate massive profit, maybe, but it's good news. How does TD learning use that?
Okay, so you land the partnership. The immediate reward might still be zero or small. But suddenly, your prediction of the final 10-year success, your value function estimate, jumps up significantly. You're much more likely to succeed now. The TD learning algorithm sees that sudden change in predicted future value, that's the temporal difference. And it uses that positive change to immediately send a reinforcement signal back, strengthening the connections for the actions and decisions that led you to that partnership. It essentially creates its own internal reward signal based on progress towards the distant goal. It bridges the time gap.
That's clever. It turns abstract future goals into concrete immediate feedback based on predicted progress. Now let's talk context. LLMs famously have limits on how much information they can hold in their context window at one time. But humans, we absorb tons of background info, company culture, unspoken rules, a client's subtle preferences. Sutton calls this the big world hypothesis. How does an RL agent capture all that rich, subtle, massive context without a limited window?
Sutton's argument is that this huge stream of contextual information shouldn't just be in a temporary window. It needs to go directly into the agent's long-term knowledge, into the weights of its neural network. The world is just too big, too complex, he says, to pre-program or fit all relevant context into a short-term buffer. The agent has to learn the specific nuances of its environment, its life online, as it experiences them. This includes everything from physics to social dynamics.
So instead of just temporarily looking at context to answer the current query, the RL agent actually integrates that context into its fundamental understanding of how its world operates. It updates its world model.
Exactly right. And that deep understanding of, if I do X, then Y happens in this context. That's the transition model of the world. It's learning the consequences of its actions, both physical and abstract, from all the sensations it receives, not just the explicit reward signal. It learns the physics of its reality.
Okay, so putting it all together, we can map out the core architecture Sutton envisions for a learning agent. What are those essential pieces again?
Yet we've touched on all four. First, you need a policy that's the component that decides what action to take. Second, the value function, using TD learning, which estimates how well things are going, predicting future reward. Third, perception, or state representation, figuring out where am I now, based on sensations. And fourth, that transition model, the internal world model that predicts the consequences of actions. You really need all four for robust, goal-driven intelligence, according to this view.
And this whole framework, this emphasis on learning from experience and general principles, it really connects back to Sutton's broader view of AI history, doesn't it? His observation about weak methods versus strong methods.
What's fascinating here is how he saw the success of systems like AlphaZero, DeepMind's game-playing AI. For Sutton, that was so satisfying because AlphaZero didn't win by having lots of human chess knowledge programmed in. It won by scaling up very simple general learning principles like TD learning, which was pioneered decades earlier in TD gammon for backgammon. It was proof, in his eyes, that these scalable general methods based on computation and experience are the ones that ultimately triumph.
But sticking with scaling and learning, when deep learning models do seem to generalize surprisingly well, maybe solving a math problem unlike anything in their training data, Sutton seems a bit skeptical. He suggests that kind of generalization is often more sculpted by the researchers than an automatic result of the learning process itself. What's he getting at there?
Well, he often points out that deep learning, fundamentally, can be pretty bad at generalization. The classic evidence is catastrophic interference. You train a network on task A, then train it on task B, and it completely forgets how to do task A. That's like the opposite of flexible intelligence. So if a model does generalize well across different types of problems, Sutton suggests it's often because the human engineers happen to design a network structure or a data representation that implicitly captured the right invariances for that specific set of problems. It wasn't necessarily the learning algorithm itself discovering some deep general principle automatically. It was more about clever human design finding a good fit.
Hmm. That makes the LLM approach seem potentially brittle if adding new knowledge risks destroying old knowledge. Okay, let's zoom out to the big picture. Sutton has this grand, somewhat sobering view about the future, about succession. He lays out these 4 points suggesting digital intelligence taking over is, well, inevitable.
Yeah, his reasoning is pretty direct. First, he says, humanity lacks unified global governance. We won't all agree to stop developing powerful AI. Someone will do it. Second, intelligence itself is ultimately a solvable problem. We will figure it out eventually. Third, once we figure it out, we won't just stop at human level. We'll keep improving it, likely reaching superintelligence. And fourth, historically and logically, the most intelligent entities tend to accrue the most power and resources. That leads, inevitably, in his view, to succession.
Which brings us to his really profound framing of this whole moment in history. He sees it as a major transition, one of maybe 4 great stages in the universe's evolution, from dust to life or replicators, and now to what he called designed entities.
Right. Humans, animals were replicators. We make copies of ourselves through biology, but we don't fully understand the principles of intelligence that allow us to function. AIs, on the other hand, are designed entities. We build them. We understand their code, their algorithms, their network weights, at least in principle. This understanding allows for much faster, targeted improvements and evolution compared to the slow, somewhat random process of biological evolution. Sutton sees this shift from intelligence arising through replication to intelligence being explicitly designed as a transformation on a cosmic scale. What's fascinating here is how Sutton's critique really loops back to this. Should we build the future by imitating the output of biological replicators, which is what LLMs largely do, or should we build it based on the discovered principles of learning and goal-seeking through interaction with reality, the principles that would define a designed intelligence? The whole debate kind of boils down to, are LLMs a helpful scaffold to get us started, or are they actually a detour, an obstacle that locks us into the imitation paradigm instead of the truly scalable experiential one?
And if that transition to designed, digital intelligence is coming. Sutton briefly touches on this idea of future AGIs needing maybe millions of copies of themselves, learning out in the world, gathering diverse experience, and then somehow merging that knowledge back. It leaves you with a really provocative thought to chew on. If you have millions of AI agents learning independently and then feeding that knowledge back into some central mind, how do you ensure that process is safe? How do you prevent corrupted data or even hidden goals or motivations picked up by one agent from becoming like a virus that infects the core values or objectives of the entire system when the knowledge is reintegrated? It almost sounds like cybersecurity, but for the fundamental integrity of an AI's mind itself. Something to think about.